Alright, so we have some other topics to discuss now that we've learned a bit about the basics of calculating probability. Example 5 is really nice because it brings up several other important terms: probability distributions, random variables, and expected value. It has to do with an experiment that's described in example 4, I believe, on the previous page. Anyway, the example is that you roll 2 number cubes, which are dice, and you just look at the faces that are up and add that. And here's an example, this little picture I've drawn. You'd get 3 and a 4, and so the total is 7. Alright, so they, using example 4 and what they learned there, they've made this table, which is a probability distribution. A probability distribution is kind of like a list or a table that shows possible outcomes and the probability of each one. They also introduced the term random variable here. Okay, well, a random variable is just anything that is subject to change sort of in a chance way. In this case, the total on the upward faces of these 2 die, that's our random variable, the sum of the faces. What example 5 asks us to do is to calculate something called the expected value. This is really useful in a lot of different situations. The expected value is kind of like the average value that you would expect, the average or the mean of the upward facing 2 dice in this case. And the way it works, you're basically going to take an average of this funny product. Okay, if you look here, you'll see I'm multiplying 2, the sum of the faces in the first column of my table, times the probability that I get that. And then I'm adding to that 3, the sum of the faces in the second column, times the probability that I get that, etc., etc. I'm multiplying the top row times the bottom row, essentially, and then I'm adding all of those together. And that's a lot of work, but if you do it, you actually get 7. And so what this is basically doing is, if you just average all the numbers, you're also going to get 7, I believe, but that's kind of a coincidence in this case because the probability distribution is symmetric. But in general, this technique of multiplying a value by its probability, what you do is you find a weighted average that takes into account the different likelihoods of each value. They don't give you a formula for this, I don't think, but right here you can see my formula for expected value. And it's just showing you that if a random variable x can have different values, you take each of the random variable's possible values xi, multiply it by the probability of getting that, p of xi, and add them all up. Alright, the next example, example 6, about the lottery, is also an expected value problem. Okay, then your book takes kind of a graphical turn to this, which I like. They start talking about something called probability density functions, and they are essentially just graphs of probability distributions. If you look at this first example here, they're showing, the probability that you're going to get a certain color marble when you pull a marble out of a bag. And so the height of this graph corresponds to the probability of each event. Example 7 is actually showing a graph of the dice problem that we just finished with the probability distribution in the table. Okay, so if you look at that, you'll see that the height of that function is the probability of getting each of those values on the horizontal axis. So for example, in that blue bar there, the chance of getting a 9, what does that go up to? Is 1 out of 9, or 4 out of 36, right? So all this is a graphical way of showing a probability distribution. Now, like we said before, in a given sample space, the probabilities of all possible outcomes have to add up to 1, or 100%, because otherwise something's funny. I mean, what that means is that something has to happen. Yeah? Either we get the sum of the faces to be 2, 3, 4, 5, blah, 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 all the way up to 12. We can't have anything else happen. One of those things has to occur. So that those probabilities have to add to 1. And the graphical analog to that is that the area underneath this graph, underneath the probability density function, has to add up to 1. Probability density functions can be kind of chunky and stair-steppy, like in example 7, or they can be smooth and continuous, like in the example shown at the bottom left here, example 8. Okay, so this is I don't really like the way most of the introduction to this section is organized. That's why I kind of departed from it at the beginning. But I think most of the examples you have to do for homework in this section have something to do with one of those examples I worked through at the beginning with the heads versus tails and the 1 through 6. Okay, so all the principles like complementary probability, mutually exclusive events, inclusive events, adding and multiplication of probabilities, those were all covered there. So if you get stuck, go back and look at my examples there if the examples in the book don't help you. Okay, so here are the problems I'd like you to work on. Some of them are tricky, they're not easy, but please send me questions if you have any trouble. Good luck, guys.